Hello everyone, I'm Yang Xu from Northwest University of China. We propose data path tracing for real-time global illumination in mixed reality. We begin with an image of the real scene captured by a camera. We want to seamlessly integrate virtual objects into the real scene. If we just render the inserted virtual objects under a high dynamic range environment map using path tracing, without considering the light interactions between the real scene and the virtual objects, we can obtain an image like this. Compared to the image considering the light interactions, we can see that there are many differences, such as the soft shadows cast by the virtual objects, the green, red, and blue color bleeding or interreflections on the white paper from the virtual objects, and the indirect illumination on the virtual objects from the white paper. But how to simulate the change of illumination introduced by the inserted virtual objects? Differential rendering can do it. First, we model the geometry, BRDF, and the light source of the real scene, and compute a global illumination solution to obtain the real radiance, LR. Then we insert the virtual objects into the modeled real scene and compute another global illumination solution for the whole scene to acquire the mixed radiance, LM. And we also need the background radiance, LB, from the image of the real scene. And the virtual object mask M. We subtract the real radiance from the mixed radiance and then add the background radiance. The result is multiplied by the inverted virtual object mask to obtain this image. The image only contains the pixels belonging to the real scene. Next, we multiply the virtual object mask and the mixed radiance, and the result only contains the pixels belonging to the virtual objects. Finally, we add the two results to obtain the composited image. This is the procedure of differential rendering. Many global illumination methods were used to render the scene in differential rendering. However, differential rendering is a two-pass method that requires computing two global illumination solutions, which reduces the rendering efficiency. One-pass differential rendering can compute and composite the radiance coming from the real and virtual objects together in a single ray tracing path by shooting two types of rays instead of rendering two separate results. Methods based on delta radiance fields can directly compute the radiance change introduced by the inserted virtual objects. We want to directly compute the radiance change caused by the virtual objects using path tracing. We assume that the real scene is just a plane and modify the standard path tracing to propose delta path tracing. In standard path tracing, if a ray is shot from the primary hit point x0 and doesn't hit the real object or the virtual object, the environment map is queried to evaluate direct illumination. Let's mark it in red. Then another ray is shot from x0 and hits the virtual object at x1. This ray is blocked by the virtual object, so we don't need to query the environment map, and we mark it in gray. Next, a ray is shot from x1 and hits the environment, so we mark it in red. In one-pass differential path tracing, the ray blocked by the virtual object should also query the environment maps to evaluate the real radiance, so we mark it in red. In delta path tracing, if a ray from the primary hit point x0 doesn't hit the virtual object, we don't query the environment map. Otherwise, if a ray hits the virtual object, we query the environment map in the direction of the ray and evaluate the radiance blocked by the virtual object. Then another ray is shot from the hit point x1, and if the ray doesn't hit the scene, we query the environment map as we do in standard path tracing. Standard path tracing is still applied to the primary hit points belonging to the virtual objects, because the background radiance from the image of the real scene is not available for the virtual objects. We use multiple important sampling between BRDF and the environment map to improve the sampling quality. We pre-compute a series of samples. At runtime, we sample a subset from the pre-computed samples, and a balanced heuristic is used in the MIS. We compare the rendering results using different sampling strategies with the same sample count, 128 samples per pixel. This is the result of BRDF in-person sampling, and we can see that the shadows and the diffuse reflections are very noisy. And this is the result of environment map sampling. We can see that the noises of the shadows are reduced, but the glossy reflections on the dragon and the glossy interreflections on the white paper have many fireflies. MIS combines the advantages of BRDF sampling and the environment map sampling. We use Vulkan retracing with the require extension to implement our delta path tracing. We show the rendering results under two different high dynamic range environment maps captured by a panorama camera. Here is the first environment map. Here is the result under the first environment map. Our delta path tracing is twice faster than one-pass differential path tracing. We can see the soft shadows cast by the virtual objects and the interreflections from the virtual objects. This is the second environment map. And this is the result under the second environment map. Our delta path tracing is also twice faster than one-pass differential path tracing. We can see the shadows and the glossy reflections of the light sources at the ceiling. Let me summarize our work. We present a modified path tracing algorithm called delta path tracing, which is suitable for photorealistic rendering in mixed reality. And we implement delta path tracing by hardware-accelerated retracing on modern GPUs to seamlessly integrate virtual objects into real scenes at real-time frame rates. Let me talk about the future work. We can improve the rendering efficiency and quality by utilizing advanced denoisers and sampling strategies. And we like to support rendering of transparent and translucent objects in the future. The real scene can also be modeled at runtime and support dynamic light sources and arbitrary scene geometries. And we also plan to integrate our method in video see-through head-mounted displays and mobile devices. Thanks for your attention.